Hey, welcome back everybody. How we all doing? Lesson 4, rational functions. Remember we talked about how in the last lesson that we could have two types of discontinuities. One, an infinite discontinuities where on a graph that's a vertical asymptote. And then the other one, which we're going to do in lesson 4 today, points of discontinuity. Okay, so that's basically what they're talking about here. And let's go down and investigate this. We have two functions here. Consider the function f of x equals x squared minus 4x plus 2 all over x minus 3, and g of x equals x squared minus 4x plus 3 all over x minus 3. State the non-permissible value of each function. So for this one, x cannot equal. So what value would cause the denominator to be 0? And that would be 3. Basically set that to 0 and solve for x. Here, x cannot equal, again, 3. So they both have the non-permissible value of x cannot equal 3. Okay, use a graphing calculator to graph y equals f of x, and then we're going to sketch it on grid 1, which I'm assuming they give to us someplace. So grab your calculator, I will as well, and put f of x into y1. Okay, did you remember to put brackets around your numerator and brackets around your denominator? Hopefully, okay. Now with Zoom Standard, resetting our windows, we get a graph that looks like that. Yuck. Okay, let's try Zoom Decimal, just so it looks a little prettier. And we get a graph like that. Not bad. I'd kind of like to see further up and down. So let's go back and change our y min to double what that is. So I'm just going to go to the end and I'm going to go times 2. Okay, and then I'm going to change and see how it automatically calculated that for me. And then I'm going to go here and I'm going to multiply the y max also by 2. And that way our Zoom Decimal thing still works pretty well. Okay, could actually change our x max, now that I think about it, to something a little bigger. So go down there, go to the end, and then go times 2 so that you have multiples of the Zoom Decimal thing. Okay, that looks pretty good. That looks pretty good. Yeah, so that vertical line obviously is not part of the graph. It's a vertical asymptote happening at, what do you think? Probably x equals 3, right? Okay, so let's go back to our thing. Okay, did they give us a grid 1 somewhere? Yes, they did, down here. So we're going to put that on there. What did our graph look like again? Oh yes, okay, let's just bring that over here so I can see it. Okay, so we have the vertical asymptote and then weird things going on. So we have at x equals 3, vertical asymptote, and then it looks something like this. Let's take another look. And then something like this. Okay, all good. Now, it says state the equation of the asymptote of f, which we already know to be x equals 3. Okay, student assumed that y equals g of x would be similar to the graph of y equals f of x with a vertical asymptote of x equals 3. So to investigate that, we're going to graph that on the calculator. So let's go back up. We're going to graph now y equals g of x in the graphing calculator and see what we get. Okay, so you guys go ahead and do that and then we'll see if we get the same thing. So g of x, really the only difference is this one number, right? Instead of plus 2, it's plus 3. So we changed that and look at what it did to the graph. You probably think you did something wrong, right? Well, no, this is what it's supposed to look like, except it doesn't look anything like the other graph. It actually looks like a linear function, doesn't it? So to answer these questions, what shape does a graph take? It takes a linear shape, okay? Does the graph have a vertical asymptote? No, it doesn't, okay? But explain why the graph must have a discontinuity, because x cannot equal 3, right? The x minus 3 factor is in the denominator. So there must be some sort of discontinuity on this graph. Well, let's take a look at our graph again, and we're going to zoom in on that place to try and Zoom Decimal and see if we can see the hole in the graph. Because right now, our graph pretty much looks like a straight line, doesn't it? Okay, let's take a look at our graph. Okay, so let's go Zoom Decimal, number 4. Oh, can you see it right here? There's like a little hole in the graph there. Haha. So we want to put a hole in the graph looks like at 1, 2, 3, and 2. Okay, so what we're going to do on here is we're going to put a hole in our graph at 3, 2, and then draw the graph the rest of the way. Let's just see if we can get, yeah, so it's crossing here at 1. So it kind of looks like this. Okay, except straight line. Okay, so this hole in the graph is referred to as a point of discontinuity. Alrighty, and it appears to be at 3, 2, but we don't know yet. We're actually going to figure out how to find that point. Okay, so next page. Okay, we have two new functions. We have a of x equals x plus 2, a linear function, and we have b of x equals x squared plus 3x plus 2 over x plus 1, a rational function. Okay, so state the domain for each function. So for a of x, our domain, well, it's a linear function, doesn't seem to have any restrictions. Hey, sorry about that glitch. I had difficulties with the program. So stating the domain, since this is a linear function, the domain for a of x would simply be x is an element of the reals. However, for the b of x function, because we have a denominator with x in it, where x can't equal -1, our domain for this one would be that x can't equal -1, but it could be anything else. So x is an element of the reals. Good. Now we're going to grab the graphing calculator again, and we'll go zoom decimal to set our windows. And we're going to graph each of these functions, and we'll graph them here. So you guys go ahead and do that, and then we'll see what we get. Okay, so pause your video, please. Okay, so in the graphing calculator, I put x plus 2 and y1, and the b of x function, the rational functions, in y2. I made it a bold line, and then I went zoom number 4 decimal, so that hopefully we can see the hole in the graph. Now, I don't know if you caught that really quickly, but the thin line, the first function, graphed underneath that, and then we have the other one on top of that. So if we just go in and shut off the first function by hitting enter on the equal sign, we would have that function. Okay, so it appears that we have a hole in the graph again, right here. Explain the difference between the two graphs. Well, the difference is their b of x has a hole at x equals -1, okay, or a point discontinuity. Okay, now what we're going to do is we're going to factor the numerator of b of x to show that the two functions are actually the same except for a restriction on the domain. So if we take b of x, which is x squared plus 3x plus 2 over x plus 1, and we factor the numerator, nice quadratic equation or quadratic function there. Let's factor the numerator. We get x times x, it multiplies to 2, 2 and 1, both positive to add to a positive 3. And then you'll notice, first of all, x can't equal -1, we'll throw that in, but then that common factor can divide, and we really just end up with x plus 2, where x can't equal -1. So you see how that's the same as a of x was equal to x plus 2, all except for the domain restriction of x can't equal -1. Now, to find the coordinates of this hole in the graph here, we know it's at -1 comma something. What we do is we replace the non-permissible value into the equation of the simplified function, or in this case, the straight line. So if we go b at -1 and we sub into our simplified function, we would get 1. So that means the point of discontinuity is going to be at -1 comma 1. Okay, awesome. So that's the best way to find the coordinates of that point that we're missing. All right, part 3. Consider the function g of x equals yada yada. Use the methods in part D and E to express in linear form, including the domain restriction, and then determine the coordinates of the point of discontinuity. So in other words, I'd like you to take g of x and factor that and simplify it. Make sure you add in your domain restriction. And then after you do that, see if you can figure out the coordinates of the point of discontinuity. Okay, so pause your video and go ahead and do part 3, please.
Okay, so we should have gotten x minus 3, x minus 1 on top. When we factored that, the x minus 3 factor canceled, but before we do that, we say x cannot equal 3. That's our domain restriction. And then what we're left with, g of x equals x minus 1, comma, but x cannot equal 3, is expressing g of x in linear form. Okay, to find the coordinates of the point of discontinuity, we know x can't equal 3. So if we put 3 into our simplified form, we get 3 minus 1, which is 2, and therefore our point of discontinuity is at 3 for x, 2 for y, and there we go. Good job. Let's take a look at the next page. Okay, so it just kind of summarizes what we've been talking about. If the numerator and denominator have a factor in common, then the graph will have a hole. And this hole is called a point of discontinuity, or a point discontinuity. Functions of point discontinuity. Okay, and it is represented on the graph by an open circle. Okay, how do we find it? We factor the rational expression, simplify it by canceling common factors, and then finally you substitute the non-permissible value into the simplified form to get the y value. Okay, typically on the graph you can't see this unless you're at zoom decimal, and hopefully it's in the region that you're looking at. And sometimes if there's multiple points, you just won't see it. So that's why we need to know how to do this algebraically. Okay, so don't think, oh, I can just do it on my graphing calculator, because no, it just won't show up sometimes. Okay, let's look at this rational function. X cubed minus 7x plus 6 over x minus 1. Okay, first write the numerator of the function as a product of 3 binomial factors and hence express in simplest form. So you'll notice with this, f of x equals x cubed minus 7x plus 6 all over x minus 1, that the numerator is a cubic polynomial function. How do we get this into 3 binomial factors? Well, guess what? Welcome to the unit on polynomials. We are going to basically factor completely x cubed minus 7x plus 6. And we kind of know already that one of our factors is going to be x minus 1. So we can use synthetic division, if you recall, and we'll set x minus 1 equal to 0 to find out that x equals 1. That's going to go here for what we're dividing into. Across the top here goes the coefficients of each of our x's in descending degree. We're missing x squared, so you have to put a 0 there, then negative 7, then positive 6. This is good review, isn't it? Okay, and carry the 1 down. Multiply 1 times 1 gives you 1, and then we're adding each of these. 0 plus 1 is 1. 1 times 1 again, 1. Negative 7 plus 1 is going to be negative 6. Negative 6 times 1 is going to be negative 6, and again we add, so we get 0. And that's what we wanted, because this is our remainder. Okay, so what we just discovered now is we now have x minus 1 as a factor, and then we're left with x squared. This is x squared plus x minus 6 plus x minus 6, and we're over top of x minus 1 still. So the only thing we have to do is factor that quadratic, which we don't need synthetic division for. We can do that normally. X times x, and then multiplies to 6, 3, and 2, adds to positive 1, so positive 3, negative 2. And there we go. So by doing that, we now have our 3 binomial factors, and hence in simplest form. Now I think what they're talking about there is we can now cancel off x minus 1, but before we do, we have to make sure we're going to tack on that x cannot equal, what's our NPV? 1, right. So our simplest form would be f of x equals x plus 3 and x minus 2 as factors where x can't equal 1. Okay, so that means when we graph this, it's not going to be a linear function because x times x is x squared, and that'll be a parabola. Okay, so determine the coordinates of the point of discontinuity. Well, to do that, we would go f at whatever our non-permissible value is. So f at 1 equals, and we sub 1 into our simplified form. And we would get 4 times negative 1, so negative 4. So our point of discontinuity, POD, is at 1, negative 4. Okay? State the zeros of the function. Well, zeros happen when the function equals 0. So if we had 0 equals x plus 3, x minus 2, our zeros would be x equals negative 3 and x equals 2. Now it would probably, we're going to finish this up in part 2 or part 3. We'll see you then.